plastic doesn't actually go away. A grocery bag buried in a landfill today will still be sitting there, largely intact when your great-great-grandchildren are alive. And the handful of plastics marketed as biodegradable usually need an industrial composting facility running at specific temperatures to break down at all, conditions that essentially never occur in a regular landfill or a patch of soil. Globally, less than 10% of all plastic ever produced has actually been recycled, and the rest has either been burned, buried, or left to slowly grind down into the microplastics now showing up in drinking water, in soil, and inside the human body. That's the trade-off the entire plastics industry has been stuck with since the material was invented. You can have something durable enough to actually use, or something that disappears afterward. But getting both in the same material has been treated as close to impossible for decades. In October of 2025, a team of researchers in China, publishing in the peer-reviewed journal Nature Communications, said they'd built a plastic that does both, and it's made almost entirely out of bamboo. The material is called BM plastic, short for bamboo molecular plastic, and the team behind it, led by Haipeng Yu and Dawei Zhao at Northeast Forestry University in Harbin, was careful to draw a distinction that matters more than it might sound like at first. This isn't bamboo fiber mixed into ordinary plastic the way sawdust gets mixed into particle board, which is how most bamboo plastic products on the market actually work today. What Yu and Zhao's team did instead was break bamboo down at the molecular level into its raw cellulose, and then rebuild that cellulose into an entirely new material with a structure that doesn't exist in nature at all. It's less like adding a natural ingredient to plastic and more like using bamboo as raw material to grow an entirely different substance from scratch. To understand how that's even possible, you need to understand what's actually holding a piece of bamboo together in the first place. Bamboo, like wood, gets its strength from cellulose, long chains of sugar molecules that lock together through an enormous number of hydrogen bonds, the same basic type of bond that holds water molecules together, just organized into a far denser, more rigid network. Those hydrogen bonds are exactly what makes bamboo tough enough to grow 20 meters tall without collapsing under its own weight. And they're also exactly what makes cellulose so difficult to work with as an industrial raw material, because breaking that bond network apart without destroying the cellulose molecules themselves has always been the hard part. The method the team used to pull it off works in two distinct stages. First, they soak bamboo cellulose in what's called a deep eutectic solvent, a mixture of zinc chloride and formic acid, which sounds aggressive but is specifically chosen because it dismantles the hydrogen bonds holding the cellulose chains together without breaking the chains themselves apart. That leaves the cellulose in a loose, disorganized gel state, still fundamentally bamboo at the molecular level, but no longer locked into its original rigid structure. Then comes the second stage, which is where the actual engineering happens. The gel gets treated with ethanol, and that ethanol acts almost like a conductor, triggering the loosened cellulose chains to reorganize themselves into a new, much denser network of hydrogen bonds than the ones that existed in the original bamboo. The entire process runs at room temperature using non-toxic, reusable chemicals, no industrial furnace, no high-pressure reactor, which is notably different from how most conventional plastic actually gets manufactured. There's a reasonable question underneath all of this, which is why bamboo specifically, rather than corn, which is already the standard feedstock for PLA, the most common bioplastic on the market today. The honest answer has less to do with the chemistry and more to do with logistics and land. Corn used for PLA is a food crop, planted annually, harvested once, and grown on land that could otherwise be used to grow something people actually eat, which is exactly the kind of tension that's made Chinese regulators nervous enough that the government has previously ordered a halt on new corn-based ethanol plants, specifically over food security concerns. Bamboo doesn't carry that same baggage. It's a grass, not a food crop at any meaningful commercial scale. It reaches harvestable maturity in 3 to 5 years, and crucially, it regenerates directly from its own root system after being cut, meaning a bamboo stand doesn't need to be replanted the way a cornfield does every single season. Some bamboo species can grow close to a meter in a single day. China also happens to already have the largest bamboo industry on the planet by a wide margin, with roughly 7.6 million hectares of bamboo forest spread across 18 provinces and more than 500 distinct species, which means the raw material supply chain this invention would need to scale already exists, rather than needing to be built from nothing. None of that would matter much if the resulting material couldn't actually perform, though. And this is the part where BM Plastic separates itself from most of the eco-friendly alternative materials that get announced and then quietly disappear. In testing, the researchers measured a tensile strength of 110 megapascals, which is roughly double what you'd get from PLA or high-impact polystyrene, two of the most common plastics it was directly benchmarked against. Its flexural modulus, essentially a measure of how much a material resists bending, came in at 6.41 gigapascals, and it remained thermally stable above 180 degrees Celsius, holding up under conditions like 7 days at 100 degrees or negative 30 degrees without cracking. According to the published research, it also outperformed carbon fiber and glass fiber composites in specific categories like sound absorption and thermal insulation, and matched them on corrosion resistance. Numbers that, if they hold up under further independent testing, would put a bamboo-derived material in genuinely unusual company for something grown out of the ground rather than refined from petroleum. And this is really where the story gets interesting, because the entire reason plastic became the default material for almost everything in the modern world is that durability. And durability has always come at a permanent cost once the product's useful life is over. BM Plastic appears to break that trade-off. According to the study, the same material that survives sub-zero cold and near boiling heat during use fully biodegrades in ordinary soil within about 50 days once it's actually discarded. That's not a hypothetical lab claim about theoretical compostability. Under industrial conditions, it's degradation tested directly in natural soil. The actual environment plastic waste ends up in when it isn't properly recycled, which describes the overwhelming majority of plastic waste on Earth right now. The material also handles the recycling question better than most plastics currently in use. The research team reported that after going through their recycling process, BM Plastic retained roughly 90% of its original mechanical strength. A genuinely strong number, since most recycled conventional plastics lose a meaningful chunk of their strength and quality every time they're reprocessed, which is exactly why so much plastic today only gets downcycled into lower grade products instead of being reused for the same purpose again and again. A material that can biodegrade completely when it's thrown away, but also hold on to most of its strength when it's deliberately recycled instead, is offering two separate end-of-life paths that conventional plastic has never been able to offer simultaneously. Here's the part of the story that usually gets skipped over in coverage of lab breakthroughs like this one, though, and it's arguably the most important question of all. A material can have perfect lab numbers and still never make it anywhere near a real product, because manufacturing it at scale is an entirely different problem than synthesizing a small batch in a university lab. This is where BM Plastic actually has a genuine answer, rather than a vague promise. According to the researchers, the material can be shaped using injection molding, compression molding, and standard machining, the exact same processes factories already use to manufacture conventional plastic products today. That matters enormously because it means a factory wouldn't need to tear out its equipment and build an entirely new production line just to work with this material. It could, in principle, be run through machinery that already exists. The researchers demonstrated this at a lab and pilot scale rather than full industrial production, so it's worth being clear that compatible with existing equipment and actually being manufactured at industrial volume are still two different milestones, and only the first one has been demonstrated so far. Now, for the part of this story that keeps it from being an unambiguous win, because a responsible look at this material has to include the economics, not just the chemistry. The researchers ran a techno-economic analysis and landed on an estimated production cost of around $2,300 per ton. For comparison, commodity plastics like HDPE, the kind used in everything from bottles to piping, have recently been trading somewhere in the range of $1,000 to $1,200 per ton depending on the region and the month. That puts BM plastic at roughly double the cost of the conventional plastic it would need to compete against, with most of that extra expense coming from the price of raw bamboo itself and the energy required to recover and reuse the ethanol solvent after each production cycle. It's genuinely cheaper than a lot of existing bioplastics on the market, which is worth crediting, but it's still a real premium over the petroleum-based plastic sitting on store shelves today. And that gap is exactly the kind of thing that decides whether a promising material stays a lab curiosity or actually reaches mass production. Costs for new materials do tend to fall once production scales up and supply chains mature, but that's a projection based on how these things have gone historically, not a guarantee specific to this material. There's also a real limitation worth naming plainly because a piece of research reporting a 110 megapascal tensile strength and a 6.41 gigapascal flexural modulus is describing a material that's fundamentally stiff and rigid, closer in character to the hard plastic used in a phone case or a car dashboard panel than to the thin, flexible film used in a grocery bag or a snack wrapper. Nothing in the published research suggests the team has demonstrated BM plastic working as a flexible film or thin packaging material, which happens to be exactly the category responsible for an enormous share of the world's single-use plastic waste. And the 50-day biodegradation figure, however genuinely impressive, was measured under the specific soil conditions used in this particular study. Moisture, temperature, and microbial activity all affect how fast any organic material breaks down. So, real-world results across different climates and soil types are still something that needs to be verified rather than assumed. China does appear to be taking this seriously at a policy level, not just a research level. Multiple outlets covering the study have pointed to a government-backed 3-year action plan, reportedly launched in 2023, aimed at positioning bamboo as a leading plastic substitute nationally, which lines up with a country that already produces roughly 3/4 of the world's bamboo and has an obvious economic interest in turning that raw material advantage into a finished, exportable product. Whether BM plastic specifically becomes the material that plan is built around, or whether it ends up as one of several bamboo-based approaches competing for the same industrial investment, is still an open question this early after publication. What actually happened here is a genuinely strong piece of published, peer-reviewed materials science, not a vague press release promising a revolution that never quite materializes. The chemistry is real. The lab results are strong enough to beat several plastics already on the market, and the manufacturing compatibility with existing factory equipment is a real practical advantage most lab-grown alternatives never get close to. But it's still a laboratory result trying to cross the gap into industrial production at roughly double the cost of the plastic it would need to replace in a form that so far only works for rigid applications, not the flexible packaging responsible for so much of the world's plastic waste. That doesn't make it any less impressive. It just means the honest version of this story is a real breakthrough with real hurdles still ahead, not plastic is already solved. If you found this one as interesting as I did digging into it, stick around, because there's a lot more genuinely strange materials science coming out of Chinese labs right now than most people realize. Let me know in the comments whether you think this actually makes it to store shelves, and I'll see you in the next one.